guys, it's your favorite reliability test guy here with another fun-filled, action-packed video on reliability tests and validation topics. This current video is an introduction to MIL-STD-810 Part 2, covering low pressure, high temperature, low temperature, and temperature shock tests from MIL-STD-810. I said in the last video that this would be about a 5-week series, but as you can see from the length of this current video, each video would be an hour or more. In order to reduce the duration of each video, I will expand this out to an 8-week series, potentially more, so that you don't experience information overload from one video. I hope you enjoy this video, and if you do, don't forget to hit that like button, subscribe to my channel, and ring that bell. Thanks for watching, and let's get started! In this video, we will cover the following tests from MIL-STD-810. Low pressure test and overview, low pressure test and equipment, low pressure test and application, low pressure test and failure modes to look out for. High temperature test and overview, high temperature test and equipment, high temperature test and application, high temperature failure modes to look out for. Low temperature test and overview, low temperature test and equipment, low temperature test and application, and low temperature test and failure modes to look out for. Temperature shock test and overview, temperature shock test and equipment, temperature shock application, and temperature shock failure modes to look out for. Woo! That's one heck of an agenda. If you haven't done so already, check out the link above for part 1 for this video series to get up to speed on the content of MIL-STD-810, a summary of part 1, and a high-level review of all the MIL-STD-810 testing. Alright, let's start off with method 500.6 on low pressure testing, starting with an overview of low pressure testing. Low pressure testing refers to an atmospheric environment with less dense gas molecules in the air. Air pressure is created by the mass of molecules moving around in the air. The more air molecules there are, the more pressure is present. However, as you move up in altitude, whether driving up a mountain or ascending in an aircraft, there are fewer and fewer air molecules, and as a result, the air pressure you experience decreases. Air is a type of fluid, just like water. You can equate air pressure to an ocean example that we will cover. Swimming at the surface of the ocean, life is good. The pressure is almost imperceivable, and you are having a grand old time. As you begin your descent to the bottom of the ocean floor, you will begin to feel the weight of the water, which causes the pressure of the water at greater depths to increase. The first thing you will experience is pain in your ears, and as you move further, you will feel the crushing force from the water pressure on your whole body. If you really are a trooper and continue to descend further, your lungs will collapse. Moving even further down, the pressure of the water will force its way into your lungs and fill your lungs back up with water. Not a fun way to die, I can imagine. This can cause nasty things to happen to objects that are filled with air or another pressurized fluid, as they will experience a phenomenon called implosion, where the pressure inside of a sealed cavity bursts outward in a vacuum environment. Now that we have defined low pressure and went over an example of how fluid pressure works, let's discuss low pressure testing. Low pressure testing is a test that simulates high altitude environments and uses specialized equipment, which we will cover shortly, to remove air molecules from inside of a sealed chamber to produce the low volumes of air at various altitudes that systems and hardware are tested to in low pressure environments. System and hardware are tested in low pressure environments for a couple of main reasons. The first is to ensure that the system can operate and that the materials used can withstand higher altitude environments, which can include temperatures experienced at this altitude. The second type of test evaluates that a system can withstand the changes in air pressure, with the most extreme type of simulation being rapid decompression, where the system is subjected to rapid reductions in air pressure. This can cause the air in the system to push out and cause the system to implode if you have not designed your system to this type of use case. Low pressure tests mainly apply to hardware and systems installed and transported in aircraft, but can also be required for ground vehicles that operate at a high altitude environment. For instance, the highest paved road in the world is Uraco, forgive me if I pronounced that wrong, volcano in southern Bolivia, which is a road leading to the summit at a staggering 5,730 meters or 18,799 feet. However, MIL-STD-810 states that for military applications, the max ground altitude considered is 4,572 meters or 15,000 feet. 4,572 meters or 15,000 feet is also suggested in altitude for procedures 1 and 2, which we will cover shortly. However, again, suggested levels in MIL-STD 810 are guidelines. Don't just copy and paste these test parameters, and ensure that you are testing to an altitude that reflects your mission profile or use case. Let's go ahead and cover test equipment used for low pressure or low altitude testing now. Pictured is an altitude chamber used for low pressure or low altitude simulation in a test laboratory. An altitude test chamber typically is comprised of a specially designed chamber that can hold a low vacuum or rough vacuum, a vacuum pump, and oftentimes comes with a heater and a refrigeration system. You might be wondering, what is the difference between an altitude chamber and a thermal vacuum or TVAC chamber? An altitude chamber typically has one stage of vacuum that simulates high altitudes within the Earth's atmosphere. A TVAC chamber contains 2 or 3 stages of vacuum, with the deep vacuum state achieved by either a turbo pump or a cryopump for the second or third stage vacuum system. This deep vacuum environment is simulating the lack of fluid or presence of the vacuum of space environments. TVAC chambers typically use liquid nitrogen for coolant to simulate temperature extremes encountered in space. Get them back on track now. Altitude chambers typically have bolt-on sealed cover plates. These are needed to help the altitude chamber maintain the vacuum state required to simulate a particular low pressure environment. If you are performing an operational test that requires cables to be ran into the chamber to both power and send operational and functional commands to a system under test, you will either need to modify the existing port cover or fabricate a new cover with connector bulkheads that allow transmission of power and signals into the chamber and to the system under test. I would recommend fabricating new plates with bulkheads and saving the factory plates for non-operational tests. A quick and dirty method is to use port plugs as pictured, and use putty to seal the gaps on the cables you are running into the chamber and connecting to your system. This can be a challenge and time consuming, as you may struggle to get a good seal, and it literally requires you to keep pressing putty into the gaps and into the cable's harness to get the vacuum within the chamber to suck or pull in the putty until all the open cavities and gaps are fully sealed. This is a cheap and dirty method and quick method from a fabrication standpoint, but can be time consuming as you press more and more putty into nooks and crannies to get a good seal and achieve the vacuum environment needed for the test. For higher altitude tests, this may not be possible, but you can try if you'd like. I've been successful sometimes, maybe you can too. Alright, let's jump into test application now for low pressure testing, and we will review the different types of tests that are suggested in MIL-STD 810H. A note to consider is to tailor the stress levels, ramp rates, and test times, and so forth specifically to your system's mission profile or use cases. Take care not to arbitrarily copy and paste any of the MIL-STD 810H levels without verifying that the test and stress levels represent your system's field use applications. This applies to all tests we will cover in this video and upcoming videos in this series, so keep that in mind. First up, we have Procedure 1, which covers storage or air transport at high altitudes. The key word here are storage and transport, which immediately indicates that this is a non-operational test. You will then need to consider your test case. Are you trying to simulate a storage event on a mountain somewhere, or are you trying to simulate transportation on an aircraft? Depending on the test case and scenario you are testing for, the altitude, temperatures, and ramp rate will vary significantly. You also need to consider if this is a validation test or a qualification test or design margin test. You may also need to consider adding a safety factor to the test to a lower temperature and or higher altitude to ensure that you have margin in your design for qualification or design margin testing. The suggested ramp rate provided for temperature is 3 degrees C per minute or 5 degrees Fahrenheit per minute. The guideline ramp rate for altitude in the low pressure guidelines is 600 meters per minute or 1,968 feet per minute. However, this procedure states that you should tailor the ramp rate from your environmental test plan based on your mission profile, and again, it's due diligence on your part to ensure that your ramp rate reflects your application or mission profile. The suggested testing duration is 1 hour based on historical data and the experience that the MIL-STD 810 authors have used for creating the guidelines for these tests. But keep in mind, one size does not always fit all, and you must verify that these tests or ramp rates and stress levels meet your application. You also need to consider if your test case requires humidity. If you're going to run an altitude, temperature, humidity test For the first time, get ready for quite the technical challenge. Remember that low temperature is achieved by removing molecules from the altitude chamber, and when you add humidity stress dimension to your test, you are injecting water vapor via a steam generator into your chamber, which can make maintaining the simulated altitude quite a challenge. Water vapor can also cause your vacuum pump to fail early, as vacuum pumps are intended to pump air and not water, and the parts within the pump can corrode and seize and break down depending on the type of vacuum pump used for the test. One last important consideration is to plan for pre and post operational tests. You need to know if anything has changed and has failed as a result of the test. The pre-altitude test will be the baseline, and the post-test will be the data collected and compared to the baseline pre-test data to check for changes or discrepancies as a result of the low-pressure test simulation. I don't want to repeat this for every single test in this video, so pre- and post functionality or operational testing should be conducted for all tests that we will discuss in this video and in upcoming videos, so keep that in mind when you're preparing for your testing activities. Next up is Procedure 2. This covers operation and air carriage in low-pressure environments. This can be either ground operation at a high altitude or operation of a system inside of a pressurized cabin on an aircraft. The suggested test altitude, ramp rates, and durations are again guidelines, and you need to tailor the test specifically to your application. I know I sound like a broken record here, but tailoring the test to your specific application is very important to remember. The steps in Procedure 2 are very similar to the steps in Procedure 1. However, you need to develop an operational or functional profile based off of your mission profile. Again, if you really want a challenge or it's part of your test requirements, you can add humidity as we discussed in Procedure 1. Jumping into Procedure 3, now we are jumping into the test where you really get to break stuff. Procedure 3 is a rapid decompression test. This is a rapid drop in air pressure, and a typical case where this would happen is when an aircraft loses its cabin pressure at high altitudes. This test could be used for testing the design and strength of a system, but may be considered for ensuring operation of critical systems during a decompression event. Suggested temperature ramp rate is 3 degrees C per minute or 5 degrees Fahrenheit per minute, as in Procedures 1 and 2. And you can use the ramp rate for altitude ascent in the MIL standard, or even tailor the ramp rate for your particular application. This initial suggestion is to test altitude set point with 2,438 meters or 8,000 feet. The duration of the initial set point dwell depends on your test requirements. However, as a guideline, you can make the soak time that it takes for your system to stabilize to temperature the dwell time for the initial set point as a rule of thumb. Once the dwell time at the initial set point is complete, the guideline parameters for MIL-STD-810 are to transition to 12,192 meters or 40,000 feet within 15 seconds. The dwell time at this altitude is for a minimum of 10 minutes. Next up is Procedure 4, Explosive Decompression. A use case where this would happen is when a small hole is blown into part of an aircraft as a result of an enemy attack. The parameters for ramp rates, altitude heights, and so on are the same as the guidelines for Procedure 4. However, the pressure drop is much more severe. It has to happen within 0.1 seconds. Yikes! That is a pretty severe and instantaneous change in pressure. Poorly designed sealed systems could definitely implode from this type of event, and you will really get to break stuff with this test. Speaking of breaking stuff, let's cover some failure modes now for low pressure testing to consider. What we will discuss is not an all-inclusive list, and you need to consider failure modes that can happen specifically for your system. So be sure to create a DFIMA and think about how your system can break and as a result of the low pressure environment. Don't know how to create a DFIMA? I got you covered. Check out the link above on a practical tutorial on how to create a DFIMA. Some of the failure modes to look out for when performing low pressure or altitude testing are: the first are system and hardware failures as a result of overheating. Remember that low pressure means less dense air with fewer molecules, so convection of heat from a system becomes more difficult. You will need to consider the additional heat load, the components and hardware that will be subjected to an environment at low pressure. The low pressure fluid in a low pressure environment results in a system holding on to more of its heat, which can wreak havoc on things such as power electronics. You should understand the temperature rise that your system will experience and do some research on multipliers that you can use for accounting for the increase in temperature as a result of high altitudes, and design your system according to and compensate for the increase in heat loads. The next failure mode we will discuss is arcing, or the corona effect, as a result of low pressure. All systems have an arcing distance, depending on the space in between the power source and the conductive circuits and the components, and the voltage level of the power source in the circuit. When you decrease air pressure, the lack of molecules in the air makes it easier for electricity to jump to opposite charged circuits and components, and the distance required for arcing events decreases significantly with pressure drop. Also, with fewer molecules in the air, it allows the molecules surrounding the high voltage source to ionize, allowing electricity to travel further distances through the air, which is known as the corona effect. This can cause circuits to have intermittent operation issues or hard failures, which can be a nuisance at best, to a catastrophic failure of a key system on an aircraft in a worst case, depending on the role and function of the system that failed as a result of the arcing or corona effect. So keep in mind the design spacing of circuits and conductive components in your system to account for low pressure environments. The next failure mode to consider is leakage of fluids or gases from inside of a sealed system. A poorly designed sealing strategy can cause fluids or gases to push out through the seals and leak out into the aircraft as a result of the pressure difference between the pressure inside of the enclosure and the low pressure environment. A great example of pressure difference of a sealed system in a low altitude environment is if you have a water bottle with the lid screwed on tightly while you are on a flight. After a few hours at the sustained altitude, you proceed to open the bottle. At best, you will hear or even feel a puff of air coming out of the bottle as the pressure equalizes between the inside cavity of the bottle and the aircraft cabin. If the pressure difference is great enough, you will end up getting sprayed with water as a result of the pushed out water that violently comes out of the water bottle as it equalizes with the cabin air. I have first-hand experience with both these water bottle scenarios. The fourth type of failure mode is warpage of a sealed enclosure or catastrophic failure as a result of implosion of a system. This can happen through poor seals, materials that are not thick enough to withstand the pressure differential, or a system that has glass pieces such as optics that are not rated for low pressure environments. This can cause very dangerous situations for the pilot and passengers, as critical systems could fail from the implosion event, or shrapnel and debris can fly out and injure anyone in the area of the system. A fifth example of a failure mode as a result of low pressure is chemical changes. Chemical changes occur when molecular bonds are broken or atoms reconfigure and form new bonds to create new molecules. High altitude environments can cause chemical changes on low density compounds and materials, so keep that in mind when designing your system. We are now ready to jump into method 501.7, high temperature testing. So let's get started with an overview. High temperature testing is used to simulate high temperature environments. You will probably automatically picture a desert location, but this can also apply to hot jungles, a system in a room full of machinery that generates a tremendous amount of heat, and a server room, which can really heat up the room very fast. High temperature testing can also be generated by functions of the system itself. So you will need to consider how your system is designed and how you will keep active and power electronics cool to account for both heat generated by the system and also various temperature ranges of high temperature that it will encounter out in the field during operation. MIL-STD-810 breaks up classification of high temperature into two different types. The first is ambient high temperature, which is where you are at deserts, jungles, machine rooms, server rooms, and so forth. And induced high temperature, which are severe storage and transportation conditions where the system is in a non-operational state, or the system may be in its operational configuration or mountain location and not in its shipping container or packaging, but the power is in a power-off state. By stating induced, it is inferred that the materials or equipment surrounding the system create greater high temperature extremes than the ambient temperatures. A great example of this is if you have ever climbed into an attic during the summer. The attic temperature reaches temperatures significantly higher than the ambient temperature outside of the attic. Let's go ahead and jump into test equipment used for high temperature testing and cover the two typical types of test equipment that are used for high temperature testing. The first piece of test equipment for high temperature testing is a convection oven, which is a box or chamber with a heating element and a fan. Scientific or engineering ovens are typically cheaper than temperature test chambers, but they do not give the versatility of temperature test chambers, such as being able to run hot and low temperature tests and the ability to perform high and low temperature cycling. High temperature testing can also be performed in a temperature chamber with a heater, a fan, and a refrigeration system, which is the route many companies go by having a test chamber that can go both hot and cold in one system in order to save on space in their test lab and to expand versatility and capabilities of their test facility. Pictured is an example of a scientific oven and a temperature test chamber. If you would like to learn more about temperature test chambers and other types of environmental test equipment, check out my video on test equipment in the link above to learn more about most of the major environmental test equipment that is used for MIL-STD 810 testing. Let's jump into applying the test procedures for method 501.7 on high temperature testing now. The procedure method that you will use depends on the mission profile that you have developed for your system's particular application. Depending on the application for your system, you may run one of the tests, or you may run all of the tests that we will cover. If you are looking to evaluate your system to storage and operational environments where the system sits in direct sunlight, you may want to consider adding a test from the method 505.7 for solar radiation testing to your environmental test plan. We will cover method 505.7 for solar radiation testing in a later video in this series. Depending on your application, you may also want to consider low humidity conditioning as well to simulate the desert climates, which is also suggested in the high temperature guidelines as well. You will need to determine when and what your system will be doing when in the high temperature environment. Will your system simply be getting transported or stored in a high temperature climate? Or will it be operated in a high temperature climate? Do you need to consider ambient high temperature or induced high temperature or both? Again, these are guidelines. Don't go copy and paste these tables and tell your boss that the test procedures are done and it's time to go home and drink beer. Nope, you need to tailor these guidelines to your particular system and its operational load cases. You might go with a cyclical test where you are cycling between higher and lower temperature set points, or you may want to soak at a constant temperature set point. You will also need to know from your mission profile how many cycles you will need to use and run for your use case. Pictured is table 501.7-1, which provides diurnal cycles for ambient air temperature and induced temperature environments. There are two design type classifications to consider based on your mission profile. The first design type is A2, which is called basic hot. These are suggested temperatures for different regions of the world and are derived from locations such as the southwestern United States, northwestern Mexico, central and western Australia, Saharan Africa, South America, southern Spain, and southwest and south central Asia. The second design type category is A1, called hot-dry. These temperature ranges primarily focus on the regions of southwest and south central Asia, southwestern United States, Saharan Africa, central and western Australia, and northwestern Mexico. You will need to determine when and what your system will be doing when in a high temperature environment. Let's cover the A2 and A1 mission profiles now. Pictured is table 501.7-2, high temperature cycles, with the suggested mission profile for the basic hot A2 design category. This includes durations, temperature at each duration, and if you're running the additional humidity stress dimension for the test, the humidity level suggested for the mission profile. This profile is called a diurnal cycle as it covers the temperature conditions in a 24-hour period for a worst-case condition day of the year. Now let's look at the hot-dry A1 category, now under table 501.7-3, high temperature cycles. Again, this table has a 24-hour diurnal cycle with temperatures and durations for each period of the 24-hour day. Notice the ambient humidity is much lower than the humidity ranges in the A2 basic hot mission profile, which creates additional failure modes, which we will discuss in the failure mode discussion for high temperature later in this video. Let's start off with procedure 1, which covers high temperature storage. This is where your system is stored in a hangar, a warehouse, or some other unconditioned holding facility that is subject to high ambient temperatures. You will need to think about whether your system will be inside of a shipping package, out of its box, sitting on a shelf or mounted in any operational configuration, such as a system mounted to a vehicle and parked in a hot garage or warehouse for long periods of time, which will help you decide whether you will use the ambient temperature levels or the induced temperature levels. You can either run this test with either a diurnal cycle based off of A1 or A2 mission profiles or a constant temperature. In terms of temperature ramp rates, MIL-STD 810H recommends using a ramp rate of 3 degrees C per minute or 5 degrees Fahrenheit per minute. You also need to consider if you will include low humidity conditioning for this test, and again, this is up to you what you need to do based on your use case and the reason for the high temperature test. Procedure 2 covers operational high temperature testing. You will want to consider the ambient temperature environments as specified in A2 and A1 for diurnal cycles and for constant temperature operation tests as applicable. Also, you can use the same suggested ramp rate for temperature or a ramp rate tailored to your specific application. Once again, consider if you will include low humidity conditioning for your test to reflect your system's mission profile. You also will need to define the operational or functional test during the high temperature stresses. As a rule of thumb, you will want to run an operational test once your system has stabilized or fully saturated at the set point temperature. However, you may also want to run your system continuously and operate even during the temperature changes. So there are two different definitions for when a system is considered to be thermally stabilized at the current temperature set point. When the system is not in operation, the system is considered thermally stabilized once the system is within the ambient temperature tolerance for the test. The guidelines provided with the MIL-STD 810H provide an air temperature tolerance of plus or minus 30 degrees C. Therefore, once the component with the greatest thermal lag or thermal inertia is within 3 degrees C of your temperature set point, you can consider your system thermally saturated or stabilized, or whatever term or lingo you use within your company internally, in order to state that your system is conditioned to the test temperature set point. For systems that are operating continuously, MIL-STD 810H defines a system thermally saturated and at equilibrium when the component with the greatest thermal lag has a change in temperature of less than 2 degrees C per hour while operating. Option 2 for a continuous operation is typically applied on a constant temperature test when the system is operating continuously at a constant temperature set point. Depending on your operational testing profile, you can use one of these guidelines as a basis for developing your high temperature test profile. Procedure 2 also suggests running at least 3 cycles when performing the diurnal cycle, but again, the number of cycles should be driven by your mission profile. The next test procedure is Procedure 3, tactical standby or operation. The intent of this test is to allow the system to soak for a period of time in a non-operational state or standby state, and then operate the system at a certain time based on your mission profile. Again, this can be a constant temperature test or a diurnal test based on your mission profile. The testing parameters that are suggested, such as ramp rate and number of cycles, is also the same as Procedure 2. Let's go ahead and cover high temperature failure modes now. High temperature testing failure modes to look out for include: number 1 is that high temperature can cause electronics to fail prematurely if the thermal design is inadequate. When ambient temperatures are elevated, less heat can escape electronic hardware, and the heat will escape the system at a slower rate, which can damage electronic components. Number 2 failure mode is that high temperature environments can also cause seals and gaskets to fail as a result of the expansion of seals or gasket material from the use in high temperature environments. This can cause fluids and gases to escape the system and can also produce safety and contamination issues in the area of the vehicle where the system is operating. On a similar note, high temperature can even cause materials to expand, swell, or become brittle, causing the enclosure of a system or component within the system to fail prematurely. For failure mode number 4, as a potential cause of some of the failure modes just described in failure mode number 3, high temperature environments may also exceed the activation energy of a material or compound, which can result in chemical changes of the material or compound and undesired effects and breakdown of the system, hardware, or component. Failure mode number 5 is high temperatures can also cause fluids that are used for lubrication to become less viscous, resulting in wear, fatigue, and early failures of moving mechanical parts and components. These are just a few examples of potential failure modes, and again, you need to create a DFIMA to ensure that you are accounting for all the potential failure modes for your particular system in your design and environmental testing plan. Alright, let's go ahead and discuss method 502.7 on low temperature testing now. Low temperature testing is used to simulate frigid environments for both transportation, storage, and operation of systems in cold environments, such as in a cold winter climate or on a high-altitude mountain where frigid temperatures are always present. It also simulates the cold temperature extremes experienced by systems in unconditioned locations on an aircraft at high altitude when parts and hardware and systems get exposed to some really cold, frigid ambient conditions. Let's cover test equipment for low temperature testing now. Pictured is an example of a temperature test chamber. Temperature test chambers come in all different shapes and sizes and have varying performance specs. Some temperature test chambers are designed to handle the heat load of large mass systems and high-powered systems using larger compressors, evaporators, and condensers. Some chambers are air-cooled and some are water-cooled for better performance and to minimize the heat expelled into the test lab's ambient airspace. Depending on the application and temperature ranges, systems can use a single-stage mechanical refrigeration system, which is comprised of a compressor, an evaporator, and a condenser. These chambers can typically go down to negative 30 degrees Celsius to negative 40 degrees Celsius depending on the size of the system. Another type of system is a two-stage mechanical refrigeration system or cascade refrigeration system. The first stage is typically called the low stage, and the second stage is typically called the high stage. These types of systems are comprised of two separate refrigeration systems that have two different refrigerant gases. The first stage removes the heat from the test chamber, and the second stage removes the heat from the first stage refrigeration system, which allows low temperatures to be achieved, and typically this type of chamber can go down to temperatures as low as negative 70 degrees Celsius to negative 85 degrees Celsius. How a cascade refrigeration system works is the first stage or low stage has a high pressure refrigerant that has thermal properties that allow lower temperatures to be achieved based on the heat removing capabilities of the overall system. The high stage has a lower pressure refrigerant and acts as the cooling system for the first stage refrigeration system. The systems are interconnected with what is called a cascade condenser, also called a heat exchanger. The cascade condenser acts as a condenser for the first stage refrigeration system and an evaporator for the second stage refrigeration system. The third type of cooling method is using LN2 or liquid nitrogen cooling. These types of systems can achieve temperatures as low as negative 285 degrees Celsius to simulate certain low temperature space and ultra high altitude environments. There are also variations on the systems just described that include mechanical refrigeration systems that have a coolant boost function that uses liquid nitrogen to extend the minimum temperature set point capabilities that the mechanical refrigeration system alone would not be able to achieve. I have a tremendous amount of experience both operating, troubleshooting, and modifying temperature test chambers. So if you would like me to do a detailed video on temperature test chambers, comment below or take the survey above and let me know. Alright, let's jump into low temperature test application now, based off of procedure in method 502.7. Let's go ahead and jump into procedure 1 for half cycle thermal shock testing. Let's go ahead and jump into temperature ranges for low temperature testing. Pictured is table 502.7-1, summary of low temperature cycle ranges. This table looks similar to the high temperature testing table that we looked at earlier. We will start off with design type C1 or basic cold. This covers locations such as most of Europe, northern contiguous US, coastal Canada, high latitude coasts such as the southern coast of Alaska, and high elevations in lower latitudes. The next design type classification is C2 or cold. This covers regions including Canada, Alaska excluding the interior, Greenland excluding the cold pole, northwestern Scandinavia, some areas of northern Asia, high elevations in the northern and southern hemispheres, the Alps, the Himalayas, and the Andes. The next design type classification is C3 or severe cold, which captures regions such as the interior of Alaska, the Yukon in Canada, the interior of northern Canadian islands, the Greenland ice cap, and northern Asia. You will need to consider which design type fits your system's mission profile, and your temperatures may be even more extreme for aircraft mounted systems that are exposed to the external environment of the aircraft. Pictured now is Table 502.7-2, which covers frequencies of occurrences for C3 severe temperature design types. Again, these are guidelines, and you may want to test to longer durations or even lower temperatures if you are looking to develop a qualification test plan for your system. The MIL-Standard 810H also provides general guidelines for operational and non-operational tests. For storage tests of a non-hazardous or non-safety related system or hardware, the standard suggests a 4-hour soak period once thermal equilibrium is achieved. For things such as explosive munitions, rubber, and plastic, the standard suggests a 72-hour soak period after thermal equalization is achieved. For restrained glass, such as with components and optics on laser systems, the standard suggests a 24-hour soak period after thermal equalization is achieved. Again, these are guidelines and not exact durations that you have to follow. Tailor the duration to your system's mission profile or use cases. Let's jump into Procedure 1 on storage temperature testing now. You can tailor your test temperatures based off of the design types just discussed and the recommended durations depending on the materials of your system. The recommended temperature ramp rate, again, is 3 degrees Celsius per minute or 5 degrees Fahrenheit per minute for reaching the temperature set point. Next up is Procedure 2, which covers low temperature operation testing. This is operating the system in its end use case based on the mission profile for your system. It could be a cyclical operational test where you have an on and off state or a standby state. The temperature equalization requirement we covered for high temperature testing, as discussed previously, would again apply to low temperature testing for determining when your system is at equilibrium or has stabilized at the low temperature set point. Last but not least, Procedure number 3. This covers manipulation of the system in low temperature environments. There are 2 options proposed for performing this test. The first is a test technician or test engineer walking into a walk-in chamber and disassembling the system once the temperature set point is reached, or to pack the system up to be shipped or transported to another location where it will be utilized. The second option is with a reach-in chamber, where test personnel will either reach through a test port or open the door to the chamber and reach into the chamber to disassemble the system, similar to the approach taken with the walk-in chamber procedure. This test may also include assembling the system and operating the system at the low temperature condition to ensure that the system is still operational. This test can also be used to simulate maintenance or service scenarios where the equipment is disassembled, repaired, and then put back together in cold weather operation. Let's jump into potential failure modes to look out for with low temperature testing now. Some potential failure modes include loss of performance or charging with lithium-ion battery systems, as the battery's battery management system or BMS will prevent operation under extreme cold weather conditions. Lubricated mechanical parts season up, wearing down quickly or rapidly fatiguing as a result of the lubrication fluid getting too viscous, turning into molasses, and not keeping parts lubricated. Undesired changes to the operation of components that can cause systems to cease to work or work intermittently. Cracking of optics as the material contracts in the low temperature environment. Condensation collecting in orifices and gaps on the system and freezing, expanding, and cracking materials on the system. Alright, let's talk method 503.7 on temperature shock testing now, starting with an overview of temperature shock testing. Temperature shock can be used as a tool to both simulate real-world use cases and to speed up failure modes. An example of a real-world use case is a jet aircraft going from a high-altitude, low-temperature environment and descending and landing in a desert environment, and vice versa. Another example would be moving a system from an air-conditioned space to a high-temperature desert environment outside of the temperature-controlled room, and vice versa, going from hot to cold. Temperature shock testing can also be used to expedite failure modes and identify both weaknesses in a design or manufacturing process, such as poorly selected components susceptible to intermittent or hard failures as a result of temperature cycling, or bad solder joints on a PCBA. I covered temperature shock or thermal shock testing in more detail in another video, so check that video out in the link above to learn more about thermal shock testing. There are typically 2 different methods that companies use to accomplish temperature shock testing, and will depend on the equipment currently available in a company's test lab and the size of the system you are testing. The first solution is to use a temperature shock or thermal shock test chamber as pictured. A temperature shock chamber has a hot and cold box that are both conditioned independently to the hot and cold temperature set points for the test. A temperature shock chamber typically has a vertical hot box and cold box configuration, with the hot box in the top chamber and the cold box in the bottom part of the chamber. There are also less common configurations as well that can have horizontal hot and cold boxes, or even 3 boxes conditioned to 3 separate temperature set points. Temperature shock chambers are great because they are fully automated and the chambers transfer between the hot and cold environments automatically, using a basket that moves between the hot and cold environments. However, temperature shock chambers are significantly more expensive than conventional temperature test chambers. Another method is a manual process of moving a system between 2 temperature test chambers, where one chamber was conditioned to the low temperature set point and the other chamber is conditioned to the high temperature set point. This is a manual process and can require multiple shifts of test lab personnel, as they will need to move the system manually between the 2 temperature test chambers. Let's discuss temperature shock test application and performing temperature shock test now. The suggested transition time per MIL-STD-810 is a transition between the hot and cold temperature environments in less than 1 minute, and vice versa. You can use the high and low temperature guidelines per section 501.7 and 502.7 for your low and hot temperatures. The procedure section under method 503.7 for temperature shock has a single procedure broken up into 4 sections, A through D. Under the initial guidelines, it states that the suggested profiles start with low temperature, but that the high temperature can be performed first as needed per your system's particular mission profile. Let's go ahead and jump into Procedure 1 for half-cycle thermal shock testing. Pictured is the half-cycle profile in Figure 503.7-1, Single Shocks Half-Cycle. This test is used to evaluate systems that will only be subjected to temperature shock on a rare occasion. It consists of stabilizing at a cold temperature and then transitioning in under 1 minute to a high temperature environment, after the system is brought back to ambient and the test is completed. The second option is Procedure 1-B, which is a single cycle thermal shock test. This again is for systems where the thermal shock does not happen too often. Pictured is the single cycle test in Figure 503.7-2. In this test, a system would soak at the low temperature extreme and then transition to the high temperature extreme and then cycle back to the low temperature extreme and soak, which equals 1 entire cycle for this thermal shock test. The system is then brought back to room ambient temperatures and then the test is completed. The third option is Procedure 1-C for multi-cycle shocks. This is for systems that are frequently subjected to temperature shocks at a high and low temperature extreme. Pictured is the multi-cycle shock profile Figure 503.7-3. This test simulates use cases such as what we discussed earlier with an aircraft descending from a high altitude, low temperature environment and landing in a hot desert somewhere, or vice versa. Again, the temperatures for these tests and the use case that you simulate will depend on the particular use cases and application for your system. MIL-STD-810 suggests that running a minimum of 3 cycles, and it is up to you to decide how many cycles you will need to run for the thermal shock for your particular system. The fourth option is Procedure 1-D for temperature shocks to or from controlled ambient temperature environments to uncontrolled and higher or lower temperature environments. Pictured is the thermal shock profile for Procedure 1-D in Figure 503.7-4. The profile demonstrates a use case where the system is moved from a conditioned room that is heated to a comfortable room temperature and then brought out into a frigid, low temperature environment outside somewhere in the winter or on a high altitude mountain. This test can also be modified to simulate moving a system from an air-conditioned room to an outside to a high-temperature environment. Again, you will need to tailor the thermal shock profile to your specific mission profile and how frequently the use case will occur moving from a conditioned space to an unconditioned environment. Let's cover some potential failure modes to look out for with temperature shock. The first failure mode is materials cracking under the rapid expansion and contraction events as a result of the rapid change in temperature. This can cause systems to start leaking if an enclosure breaks, or can even cause systems to fail if a material that is critical to the operation fractures or breaks due to the mechanical stress imposed by the rapid changes in temperature. As touched upon earlier, the rapid changes in temperature can also cause susceptible electronic components and solder joints to fracture or break, which can create intermittent operation of a system or a hard failure. Temperature shock can cause glass containers or optics to break. If you have ever poured cold water into a heated glass, you may have experienced this type of failure firsthand, which is why it's important to design glass components to withstand the mechanical stresses induced by the temperature shock events. Another failure mode that temperature shock can induce is to cause moving mechanical parts to bind, seize, or break, as well as a result of the rapid contraction and expansion of the moving parts. Temperature shock can also cause seals to fail and allow gas or fluid to leak out of a system. Again, these are just a few examples, and you will want to create a DFIMA to capture all of the potential failure modes that can occur as a result of temperature shock for your particular system. And that's it, folks! Some key takeaways from this video are: low pressure testing can simulate transportation, storage environments, and operational use cases. Low pressure testing can drive out mechanical and electrical weaknesses in your system that are susceptible to high altitude environments and even cause seal systems to implode, so look out for that failure mode. High temperature testing can also be used for simulating hot weather climates, such as deserts and jungles, but can also be used to simulate environments for rooms with machinery that generate a lot of heat, or a server room. High temperatures can bring out weaknesses in your thermal management strategy for your system, cause poor seals to leak, and cause electronic components to fail that are susceptible to high temperatures. Low temperature testing simulates frigid cold weather conditions, either in the winter or at a high altitude location or on an aircraft. Cold weather can cause lubrication on moving parts to become too viscous and cause moving parts to seize or wear out prematurely. It can cause lithium-ion batteries not to operate or charge if the thermal management for the battery cannot keep up with the low temperature conditions of the ambient air in order to maintain an operational temperature for the battery. Temperature shock simulates rapid changes in the temperature environment. It can cause weaknesses in systems and materials that are susceptible to temperature cycling to get exposed more quickly, and the test can also simulate certain operational use cases, such as moving from a temperature-controlled environment into a high temperature or low temperature environment outside of the temperature-controlled room. As you can see, we learned about the equipment needed for these tests. There are a number of types of systems that you can use. Some of the equipment is more expensive, while other equipment is cheaper but more labor-intensive, as was the case with the temperature shock chamber, or using two separate temperature chambers to perform temperature shock. Use MIL-STD-810 as a guideline for developing your environmental test plan, and do not treat the standard as a procedure that you can just arbitrarily use. So don't go and copy and paste levels and tables out of MIL-STD-810 without tailoring the test to your particular mission profile. Thank you for watching this video. If you have any questions or comments, or need help developing environmental test plans, test procedures, or executing environmental tests per MIL-STD-810, feel free to reach out to me at the link above. I hope you enjoyed this video, and if you did, don't forget to hit that like button, subscribe to my channel, and ring that bell. Thanks again for watching, and enjoy the rest of your day.